Imagine yourself standing in a log cabin in the middle of nowhere right at the height of winter. In the log cabin is a heat source, a heat lamp. You know that the closer you stand to this heat lamp, the warmer you'll be. The farther away you stand from this heat lamp, the colder you'll be. Logically, you think that the moons that are the farthest away from the sun, the heat lamp, must be cold, dead, and dull worlds. But logic has to sometimes be thrown aside in the complex worlds of physiology and astronomy. You may be colder the farther away you are from a heat lamp, but you're not dead. So you actually produce heat internally and are therefore at least somewhat warm. The same is true of celestial bodies, like the moons, that are far away from the sun. They may be cold, but they're not dead, and some of them are at least somewhat warm due to their own sort of physiological processes. This lesson will explore Jovian satellites, the moons of the four outer planets, and explain the forces that affect the heating of satellites, including internal processes and external factors like planets. One of the forces that affects the heating of a satellite is known as tidal heating, the heating of a celestial body, such as a satellite, when the shape of the body changes thanks to tidal forces. One of Jupiter's moons, Io, is a good example of what that definition really means. Just watch the images on the screen to see what happens. A moon's shape will deviate due to the tidal forces from its planet. The tidal force will increase as the moon approaches its planet, and it will decrease as it moves away from its planet. This means that when Io is closest to the planet, its shape will be most distorted. When Io is farthest away from the planet, its shape will be least distorted. This constantly changing shape causes internal friction to occur in the moon. This internal friction heats the moon. I know this may still be confusing, but here's a more familiar example. If you were to go out and take a basketball out of your garage, representing a moon, it will be cold to the touch at first. Now, bounce the basketball around for a bit. As you bounce the basketball against the ground, its shape, like that of Io's, will be distorted. This distortion causes compression of the ball, which will heat the air within it. Because tidal heating depends on the tidal force, the size of the moon and the mass of the planet it orbits will influence the rate of tidal heating. That and orbital distance. The farther away a moon is from its planet, the smaller the tidal force. What this is basically saying is that tidal heating is only truly important for large moons that orbit close enough to massive planets. Now here's something pretty interesting. The tidal interactions that occur between a moon and its planet will actually minimize the eccentricity of that moon's orbit. This basically means that a moon orbiting a planet on its own will eventually achieve a circular orbit due to these tidal interactions. When such an orbit is achieved, the moon will not change shape and tidal heating would cease as a result. The key to understanding why tidal heating can continue in some of the Jovian satellites in spite of this is orbital resonance, orbital periods of celestial objects related in such a way that they affect one another gravitationally. This means that while a single moon may go from an elliptical orbit to a circular one, when it's orbiting alongside other moons, then the gravitational attractions between it and those other moons will cause it to remain in an eccentric orbit. That's pretty much it. As a case in point, Io, Europa, and Ganymede, three of Jupiter's moons, orbit in such a way that they all influence one another to keep each other in elliptical orbits. Now, let's get back to our cabin example, where we compare the body of a moon to the body of a person. You know that the rate and amount by which you become hot not only depends on internal generation of heat through metabolism, which is like our tidal heating, but also on how quickly you can let heat escape. So, if you wear many layers of clothing, preventing the escape of too much heat, you'll become hotter faster than had you been standing in the cold in your underwear. Therefore, heat transfer is just as applicable when talking about how hot a moon can become. It's not just about tidal heating alone. The two most important heat transfer processes involved in influencing the temperature of a satellite are convection and conduction. Conduction is the thing you experience when heat transfers from a hot cup of coffee into the handle of a previously cold spoon placed into it. Convection is like the mixing around of colder and hotter regions of a fluid, as if by a spoon when you're cooking some soup. Thus, it is conduction and convection alongside tidal heating that determine how hot a satellite can actually become. How hot a Jovian satellite becomes is largely determined by conduction and convection, as well as tidal heating, the heating of a celestial body, such as a satellite, when the shape of the body changes thanks to tidal forces. Tidal heating depends on a large enough moon maintaining an elliptical orbit close enough to a massive enough planet. The elliptical orbit necessary for this would disappear if it were not for orbital resonance, orbital periods of celestial objects related in such a way that they affect one another gravitationally, meaning if moons didn't distort one another's orbits around a planet, then tidal heating would not occur. But don't forget that the temperature of a Jovian satellite isn't influenced solely by tidal heating. The way heat flows to the surface and escapes is important in regulating the satellite's temperature. The two most important heat transfer processes involved in influencing the temperature of a satellite are convection and conduction.